Okay, so in the last video, I introduced quantifiers and how to negate them properly. This is very important in mathematics because oftentimes we will give a definition of something in mathematics, and that's like the positive version or something, and but sometimes you want to prove that something does not satisfy that definition, and so you need to know what it means to satisfy the not of the definition, right? So in this video, I want to continue that sort of exploration, but I want to use examples specifically from real analysis. So this is something that when you take MAT 320 at Lehman, you will see these definitions very carefully given with all the explanation of what they mean. Here, I just want to stick to the definitions themselves. I'm not going to try to explain to you what they mean per se. I just want to show you what the definitions are and practice negating the definitions. And the hope is that when you see these definitions again in analysis in MAT 320 at some point in the future, then you will be more prepared to handle those definitions. Okay, so first of all, the first couple of definitions I want to introduce and then negate involve sequences. So you've seen sequences before. Well, if you've taken calculus 2, you've seen sequences, but you may not have taken calculus 2 yet. So let me just very quickly introduce the idea. It's a very simple idea. So I'm going to use these curly brackets here around S sub n, where n is going to be a natural number to denote the collection of um, values, one for each natural number, and so be a sequence of real numbers. We've been playing with the real numbers already, sort of. And so, what's an example of such a thing? Well, the sequence could be given by 1 over n. So, when n equals 1, the sequence value is 1. Let me try to write this a little bit differently. So, every sequence will have the first value, the second value, the third value, fourth value, the fifth value, and so on and so forth. But if I give you a particular sequence, then I can say that the first value in this case is 1 because it's 1 over n. The second value is a half, 1 over 2, and it's a third, 1 over 3, 1 over 4, 1 over 5, 1 over 6, 1 over 7, so on and so forth, right? Where in this um, we have n equals 1 and n equals 2, n equals 3, n equals 4, n equals 5, n equals 6, n equals 7, so on and so forth, right? And then, anyway, I can consider some other sequence. Maybe it's n minus 1 all over n, for instance. Now, when I go to look at this, when I plug in n equals 1, I would get 0. And then when I plug in n equals 2, I would get a half again. When I plug in n equals 3, I'll get 2/3. When I plug in n equals 4, I get 3/4. Plug in n equals 5, I get 4/5. Here I get 5/6, 6/7, so on and so forth. Okay, and you know, most likely you have at least some idea of what it means for a sequence to converge. Usually people do without needing the definition, and the definition is really there for the examples that are not so clear, but that are not so obvious. So, but anyway, in this case, um, you will probably guess that this sequence converges to 0 as because the sequence seems to be getting smaller and smaller. By the way, forgive me for all these funny squares and underlines. I think my notebook has changed versions and now it starts doing all this annoying things. I have to figure out how to turn that off, I suppose. But anyway, it's not such a bad thing. So that first sequence converges to 0 because as you go along, it's getting closer and closer to 0, right? Now, in analysis, we're going to want a more careful, rigorous definition than that, but it's helpful to have intuition first. And in the second sequence, it's converging to one because the fraction is always slightly smaller than one, but getting closer and closer to one, right? 6/7, 7/8, 8/9, 9/10, 10/11. The smaller the denominator gets, the smaller the pieces of the pie are, and you have almost all of them. You're always just missing one piece of the pie, right? 10/11, you've broken up the pizza into 11 pieces, and you have 10 of them, but that means the one that's missing must be pretty small, right? And if you keep going like this, 999 out of 1,000, you break up a pizza into 1,000 pieces, and you're only missing one piece. You have, a lot of the pizza in front of you. Okay, that's all intuitive stuff, right? But now let's look at the definition of what it means for a sequence to converge rigorously. So we say that Sn converges to L, where L is some real number, via the following definition. So for all epsilon bigger than zero, epsilon is something you're going to see in analysis a lot. For all epsilon bigger than zero, there exists a natural number, capital N, so that for all n bigger than that capital N, we find that if I take the difference between Sn and L, I get something smaller than epsilon. Again, when you take real analysis, possibly with me, I will give you, or someone will give you, a very intuitive description of what this definition means. Here, I just want to focus on taking the definition and then negating it. Okay, so for now, I'm not going to try to explain the semantics of what this definition means in terms of sequences. Instead, let's try to see what would be the definition of Sn not converting to L. The notation, we can just put a little slash through basically any mathematical symbol, and that will always stand for the not in the just in the notation itself. But then if we want to know what the definition is, well, the cheating way, or it's not really cheating, but um, it's not exactly helpful. But to start, you could just say, well, it's just the not, right? Just take the not, and okay, sure. But then, of course, in order for this to be useful, we're going to push the not through the expression like we did in the last video and figure out what the definition is without just this not out front. Okay, so when we push this through, this will be logically equivalent to the for all becomes a there exists an epsilon bigger than zero. And then usually we put the such that here now, such that for all capital N in the natural numbers, now I have to consider every natural number. There will exist a small n, which is bigger than capital N, so that now all the other ones were negating quantifiers, so it never negates the inequality or what it's in, because if you say for all epsilon bigger than zero, the opposite is to say that there exists something bigger than zero. But here at the very end, it really does negate the inequality, because that last piece is just a naked inequality at the end. And so here we go. This is what it means now. This is the useful definition, if you will, of what it means to not converge, for a sequence not to converge. Okay. And this will be very important in analysis. It'll be very important in other classes too. It's just in analysis, you tend to see a lot of definitions with multiple quantifiers. Notice this definition has 3 quantifiers in it. You'll see definitions with maybe even 4. I don't think you'll see 5, but you might see 5. But three and four are already a lot of quantifiers in a row, and that's part of what makes analysis very difficult when you start out. It's just keeping track of all the quantifiers and getting used to keeping track of all the quantifiers. So I'm hoping that if you get used to just negating the quantifiers and working with the definitions in that way, that when you get to analysis, you'll at least have a little bit of a leg up on working with these quantifiers, right? Okay. But that's what makes analysis hard. I think it's just how many quantifiers you have to work with all the time in definitions. Okay, so let's keep negating definitions from real analysis. Okay, so the next one that I want to look at is you can also talk about a sequence converging to infinity. So, for example, before I go into the definition, you could have the sequence which is equal to n squared, right? And that sequence would be 1, comma 4, comma 9, comma 16, comma 25, 36, 49. What am I up to now? 64, so on and so forth, right? So that's just n equals 1, n equals 2, and I'm just squaring because that's what the sequence tells me to do, and so on and so forth. Okay, so that's just an example of a sequence that converges to infinity, or a lot of times we say diverges to infinity in this case. Um, so what does the definition look like carefully, right? So now I don't want, so usually in analysis, we think of epsilon as something small. The definition just requires epsilon to be something bigger than zero, but the intuition is that epsilon should be something small. If I'm trying to let something go to infinity, though, I don't want to think about it as small, so I don't want to use epsilon. So I will use capital M as something that, again, it's going to be a real number bigger than zero, but now I want to think of capital M as being big, which is funny because the definition doesn't really know the difference. Epsilon is bigger than zero, capital M is bigger than zero. You know, it's those are just equivalent as far as the definition is concerned at this point in the game. But as human beings, we have to put a little bit more significance on the definitions than that. That's just how we operate. So I want you to think about capital M as something big here, but also we're just kind of in this video, we're really just operating on the syntax level since I'm not really explaining what these things mean. So you'll see more of that in 320. But anyway, so for all m, capital M bigger than zero, there exists some capital N, that part's similar, so that for all n bigger than that capital N, um, we find that Sn is bigger than capital M. It's capturing this idea that you have to get bigger than any m, basically. The sequence has to get bigger than any m in order to go to infinity. Okay, but this is the definition. So now the question is, what is the corresponding definition of what it means to not converge to infinity, right? Well, we don't really have to understand the definition to do this, right? I just put a not out front. I can just play the syntactic game here and figure out what the corresponding definition is. I'll take out the words there at the end. So what is that logically equivalent to? Well, it's equivalent to the fact that there exists an m bigger than zero, such that for all m, there exists an n bigger than that capital N, so that Sn is less than m. And I don't need this parenthesis. Okay, so now we would say that this is the definition of what it means for a sequence to not converge to infinity. And that's the one that if I asked you in a class to prove that a sequence does not converge to infinity, then this is the definition you would try to satisfy, right? And above, if I asked you to show a sequence does not converge to L, then the definition in green is the one that you would try to satisfy, right? That's why this is useful. This is why it's important to be able to do these negations so that you can understand what you need to prove in a particular exercise. Okay, so those are two definitions related to sequences. What about a definition related to functions? And actually, at the very end of this course, we're going to talk a lot about functions. But I think I can talk about it now because you have some idea of what a function is. And so let me just play with this definition. So let me take a subset of the real numbers, and I want to consider a function from that subset R. I'm using D for domain here, so I don't have to use letter D. And I want to consider some element, some value in D. Okay. So let me just give you a simple picture. D could just be an open interval in the real numbers, and then this and C could be somewhere inside of there. And then F could just be some function defined on that domain, right? So there's a simple picture. And I want to look at the definition of what it means for F to be continuous at C. Okay? So that's what we're going to look at. Again, I'm not going to try to explain all the meaning behind this definition. I just want to play with it as a syntactic definition and then negate it as practice. Okay. So what does it mean for F to be continuous at C? Okay, here's the definition. For all epsilon bigger than zero, there exists a delta bigger than zero. Again, two quantifiers already, such that for all x in D, there's your third quantifier, but this quantifier comes with a further condition where x minus c is less than delta. There you see the delta come in. We find that the difference between f of x and f of c is less than epsilon. Okay, so here's the definition. Um, this is the definition of what it means to be continuous at C. And now I want to look at the definition of what it means for um, F is not continuous at C. Okay, so for that, we need to throw a not through this expression, right? Through all these quantifiers and things. So I want to put a not here. For all epsilon bigger than zero, there exists a delta bigger than zero. I'm going to get rid of some of the words. They're just there to appease us in some sense. Okay, and so that is going to be logically equivalent to when I place this not through, I get that there exists an epsilon bigger than zero, such that for all delta bigger than zero, there exists an x in the domain where x minus c is less than delta, and f of x minus f of c is bigger than or equal to epsilon. Let me just comment on one thing that happened here. There's sort of and this happens a lot in mathematics, which can frustrate students, I think. There's sort of implied parenthesis here on the quantifier. So it's for all x with this condition that x minus c is less than delta. And that's why when I go to negate it, I don't negate this inequality either. Um, because again, anytime I negate a quantifier, I just change for all to there exists or there exists to for all, but I don't negate the inequality involved in it. Because what this part for all x in D where x minus c is less than delta is doing is telling me which x's I'm considering in that quantifier. So again, when I negate it, I'm still considering the same x's. I just want to change whether I want for all or there exists. And it's not until the very end that I get a difference in the inequality because that last condition is just a inequality condition and that gets negated straight up. Okay, so this is what it means to not be continuous here. There exists an epsilon such that for all delta, there exists an x where x minus c is less than delta, and f of x minus f of c in absolute value is bigger than or equal to epsilon. Okay, very good. So that gives you three examples from analysis. Maybe I'll do one more example of just like taking these kinds of definitions. So what does it mean for f is what we call uniformly continuous on D? So now you don't say what it means to be uniformly continuous at a point. You just want to talk about uniform continuity on the entire domain. So let's see, what does that mean, right? So for all, it's going to start off very similarly. So for all epsilon bigger than zero, there exists a delta bigger than zero, such that for all x and y in D, where x minus y is less than delta, we find that f of x minus f of y is less than epsilon. So this is what it means to be uniformly continuous. There are now actually four quantifiers because even though I only see three quantifiers, I'm quantifying technically over four variables, right? Epsilon, delta, and then x and y. But since the x and y are both for all, we combine them into one quantifier, but technically those are four quantified variables there. So we see a definition with four quantifiers now. And so let's think about what it means now to say that f is not uniformly continuous on D. Okay, so we got to send a not through this expression for all epsilon bigger than zero. There exists a delta bigger than zero. I'm going to remove some of the words such that for all x and y in D, where x minus y is less than delta. Remember, there's sort of implied parentheses here over this. Um, we find that f of x minus f of y is less than epsilon. Okay, so this will be logically equivalent to, again, these implied parentheses are there because the quantifier is telling you take all x and y that satisfy a certain condition and not just taking any old x and y. So that quantifier is over that entire condition in green here. And so what do we get? There exists an epsilon bigger than zero, such that for all delta bigger than zero, there exists an x and y that are in the domain that satisfy this restriction. And that's, I don't replace the inequality there because um, all of this is used to quantify where the x and y live. And then it's the very end thing that gets switched, right? So that the difference between these two is actually now bigger than or epsilon, bigger than or equal to epsilon. So now the this is the definition of what it means to not be uniformly continuous. And again, this part was this whole piece was telling me what the quantifier was doing. Okay, very good. I hope this is making some sense. And again, I just want to emphasize that you should not expect to understand what these definitions mean through this video. That's not the goal. I didn't try to do that. It would take much more time. Each one of these definitions in MAT 320 will be taking an entire class period to talk about or more. So I just want to remind you that you have plenty of time to learn about these things much more carefully in analysis. You'll take several days um, in that class, and most of the class will be about understanding these definitions. But I hope that by practicing negating these definitions, you will get a leg up in that class. Okay, great. So That's it for today, and we'll move on to the next chapter.